We're going to pick up where we left off with talking about gases. Remember, the four things we need to describe a gas are pressure, volume, number of moles, and temperature to fully describe what the situation of that gas in there. Again, we don't need to know what the identity of the gas is. I'm going to talk you through three laws, and these laws take two of those four variables and kind of look at them thoroughly. So for instance, we're going to start actually with Boyles Law, and we already looked at Boyles Law. Boyles Law is the relationship between pressure and volume. And I kind of talked you through, remember this, what's the name for this thing? This is called the proportionality symbol. So the proportionality symbol, in this case, we're saying that volume is actually inversely proportional to pressure, or volume is proportional to the inverse of pressure. So in other words, whenever you see that sort of situation, the way it works is if one goes up, the other goes down. They're directly opposite. That's what inverse means. They're directly opposite. And this sort of makes sense. For instance, if you have a balloon and here's my balloon. Oh my goodness, that's an ugly balloon. And I go ahead and I have the same number of moles in, but I squeeze it somehow down to here. So here I have a smaller volume. So volume is smaller. Can you imagine that pressure is greater? We've squeezed those particles into a smaller volume. So that's what we mean. Volume went down, pressure went up. So there's a neat thing, there's all sorts of neat things in math. And one of the things, if you have a proportionality symbol like this, and you want to replace it with an equal sign, you can do that if you introduce a constant. So here we go. We're going to introduce a constant, and we're simply, for now, if it's okay with you, we're going to call it a generic K. And what this says is that for the pressure and the volume of a gas, you multiply them together and they need to be equal to some constant. So let's do a little check here. If pressure goes up, does this make sense that volume must go down to keep the same constant? If pressure goes down, volume must go up because the product, the multiplication of both of those needs to be some constant. So that's how that works. I've got several sort of kind of diagrams to show you this inverse relationship between pressure and volume. Now, sometimes the tricky part, I think, in these is to identify where the gas is. So this is an old-fashioned tire pump, and our gas is contained here. So can you see where this is I'll call this V1 and I'll call this V2. Can you see where the volume here is a lot smaller in the second one than the first one? So does this make sense that the volume went down and the pressure went up? Okay, compared to the situation over this first situation here. Okay, what else we got? So you decrease volume, you increase pressure. In this case, we are actually increasing pressure by adding, this is liquid mercury, HGL, liquid mercury in here. We're increasing the pressure by adding more mercury, and pressure increase, what should happen to the volume? The volume decreases, and so it does right here. Our gas of interest is right here, our gas of interest is right here. So if we call this 1 and we call this 2. Okay, so that's kind of what we're talking about here. This is a neat little thing. We have these little particles, gas particles here, gas particles here. N is constant. What is N? N is the number of moles, and it's happening at the same temperature. So N is constant and T is constant. So this, remember, is a plunger that moves up and down. We can tell that we have more, how can we tell that we have more pressure between the two of these? P1 is less than P2 because this is a bigger weight. Does that make sense? So it's the function of how much this plunger moves down is this mass up here. This is kind of clever. We have this little sidebar chamber here to kind of show you what the pressure is. And here we have the pressure deflected this much, and here we have the pressure deflected this much. So, okay, so in this case, what looks like we we increased pressure, and we decreased volume. All right. Now, these are a series of slides that kind of make me giggle. This is actually a type of flask that we use this semester. I sometimes call it what kind of flask is it? I sometimes just call it an E flask, but it's an Erlenmeyer flask. I'm not going to try to spell Erlenmeyer right now because I probably totally butcher it. But this is a special Erlenmeyer flask. It's got a side arm. It's thick-walled so that we can go ahead and the thick-walled glass means that we can create a vacuum and apply positive pressure. So the gas of interest is actually held in this syringe. So this is the gas of interest, okay? So we're going to do a few things with this sidearm flask. Here we go. So first off, can you see where, oops, let me go back. All right. So here's this. Okay, I'm going to ask you to look at that volume. It's like a magic show. What's the volume do compared to here? How would you describe this new volume? Well, to me, that volume went down. Right? Volume decreased. So here we go. This describes why it decreased. Actually, here, this is connected to a pump, and we increase the pressure using that pump. So P increase, V decrease. You see how that inverse relationship is? All right, what else we got? Oh, then what's this? Okay, the volume continued to decrease even more. Okay, because we continue to increase the pressure going to the chamber using our tire pump. Okay, so continue to increase pressure, the volume decreases. I like this. No marshmallows were harmed, okay, but it's going to look like they were. So one of the cool things about marshmallows is that they're very sugary, but aside from sugar, they have a bunch of gas particles in there, okay? So here we go. I can't remember what I do next. Oh, yeah. Now, we're not using tire pump to increase the pressure, but we are actually using a vacuum pump to decrease the pressure, okay? If we decrease pressure, what should happen to volume? Volume should increase. Do you see the volume increasing here? I'm going to go back and forth. That's those. That's those. Volume increasing. Isn't that cool? Okay. Well, you know what I'm going to do next is now we're not going to use a vacuum. We're actually going to go ahead and change it and put our tire pump back. Okay, so now we are going to increase the pressure, and what happens to volume? Well, if we increase pressure, volume should decrease. And does it look like the volume decreased here? Joop. Joop. Isn't that neat? Makes you want to go try it, doesn't it? I just think that's so cool. Okay, so I have a few slides here. We'll continue to talk about how pressure and volume are what we say inversely related. So in this case, we have a movable syringe. Here's the gas of interest right here. And what we're going to do is actually go ahead and add shot to this little cup up here. So this is kind of their starting point. Notice on this plot, what we're going to do actually is plot the inverse of volume versus the mass that is going to be in this cup right here. The mass is actually related to or proportional to the pressure. So here we go. So this is with no mass up here, no shot up here, and here's our gas. Now see and we actually have a number to go along with that. 14.3 milliliters. Now if you take the inverse of 14.3, you get 0.075. All right. Now we go ahead and we add 500 grams of shot right there. And now I'm going to go back and forth. Check that. Here's the volume, and then here's the volume. So we increase the pressure and we decrease the volume. Oops, sorry. We decreased the volume. We decreased the volume, but actually the inverse of the volume went up. So that's kind of what you're seeing there with the trend. So let's go a little bit more. Okay, we added another shot of 500 grams, total of 1,000 grams. Increase the pressure, decrease the volume, increase the pressure, decrease the volume. Okay, so yeah, I hope that worked for you. Now this line is pretty exciting, this nice straight line, but the reason it's a nice straight line with a positive slope is because we were actually plotting the inverse of volume, not volume itself. Okay.